Hello and welcome to my channel. Today we will see some amazing facts and mysteries behind antimatter, so without any delay, let's get started. Before going to the mystery of antimatter, first let's discuss what is antimatter. Antimatter is the opposite of normal matter. More specifically, the subatomic particles of antimatter have properties opposite those of normal matter. Antimatter was first predicted in 1928 by English physicist Paul Dirac. Dirac put together Einstein's special relativity equation, which says light is the fastest moving thing in the universe, and quantum mechanics, which describes what happens in an atom. He discovered the equation worked for electrons with negative charge or with positive charges. Just as the equation x squared equals 4 can have two possible solutions, x equals 2 or x equals minus 2, so Dirac's equation could have two solutions, one for an electron with positive energy, and one for an electron with negative energy. To better understand antimatter, one needs to know more about matter. Matter is made up of atoms, which are the basic units of chemical elements such as hydrogen, helium or oxygen. In the heart of an atom, called the nucleus, are protons, which have a positive electrical charge, and neutrons, which have a neutral charge. Electrons, which generally have a negative charge, occupy orbits around the nucleus. The orbits can change depending on how excited the electrons are, meaning how much energy they have. In the case of antimatter, the electrical charge is reversed relative to matter, according to NASA. Anti-electrons, called positrons, behave like electrons but have a positive charge. Antiprotons, as the name implies, are protons with a negative charge. These antimatter particles, which are called antiparticles, have been generated and studied at huge particle accelerators such as the Large Hadron Collider operated by CERN, the European Organization for Nuclear Research, NASA stated. Antimatter is not anti-gravity, NASA added. Although it has not been experimentally confirmed, existing theory predicts that antimatter behaves the same to gravity as does normal matter. Antimatter particles are created in ultra-high-speed collisions. In the first moments after the Big Bang, as the universe cooled and expanded, particles of both matter and antimatter were produced in equal amounts. Now the question that came in our mind is where all the antimatter go? If it is created in after the Big Bang and why matter came to dominate? Well, this is a mystery that scientists have yet to discover. At the beginning of time, just moments after the Big Bang, numerous particles came into existence. At the same time, an almost equal number of antiparticles appeared. These subatomic exotics are nearly identical to their ordinary particle kin, but differ in some key ways. When matter and antimatter meet, the two annihilate one another, which means that the dawn of the universe included a spectacular microscopic fireworks display. Antimatter is sort of like a mirror to ordinary matter, having the same mass but an opposite charge. Neutrinos, which have no charge, are thought to be their own antiparticles, although experiments have yet to confirm this theory. When astronomers train their telescopes out into space, they don't see antimatter stars nor any large pockets of antimatter anywhere in the cosmos. The reason for this lack and the fact that the universe seems to be comprised entirely of particles and not antiparticles, was called one of the great mysteries in physics. Researchers are diligently seeking the factor that explains the dominance of matter over antimatter in our cosmos. Calculations suggest that just after the Big Bang, when particles and antiparticles annihilated one another, there was a slight imbalance in their numbers. Less than 1 in every billion ordinary particles survived the melee and went on to form all the matter around us today. But the question is, why? Scientists worldwide are working to determine if a neutrino acts as its own antiparticle, which would have allowed a small fraction of neutrinos to transition from antimatter to matter at the universe's inception. In this scenario, a slight matter imbalance would have existed back then. Antimatter has been created and sustained in small quantities in particle physics laboratories, but that quantity is insignificant. According to website FAQ from the CERN laboratory of CERN, scientists took all the antimatter they ever created and annihilated it with matter. They would barely have enough energy to light a single electric light bulb for a few minutes. Antimatter cannot be stored in a container made of ordinary matter because antimatter reacts with any matter it touches, annihilating itself and an equal amount of the container. Antimatter in the form of charged particles can be contained by a combination of electric and magnetic fields, in a device called a penning trap. Scientists claim that antimatter is the costliest material to make. In 2006, Gerald Smith estimated $250 million could produce 10 milligrams of positrons, equivalent to $25 billion per gram. In 1999, NASA gave a figure of $62.5 trillion per gram of antihydrogen. This is because production is difficult, only very few antiprotons are produced in reactions in particle accelerators, and because there is higher demand for other uses of particle accelerators. According to CERN, It has cost a few hundred million Swiss francs to produce about 1/1000th of a gram, the amount used so far for particle/antiparticle collisions. In comparison, to produce the first atomic weapon, the cost of the Manhattan Project was estimated at $23 billion with inflation during 2007. Several studies funded by the NASA Institute for Advanced Concepts are exploring whether it might be possible to use magnetic scoops to collect the antimatter that occurs naturally in the Van Allen belt of the Earth, and ultimately, the belts of gas giants, like Jupiter, hopefully at a lower cost per gram in the future if we able to develop such a technology which allows us to make antimatter in a sufficient amount, then we can also use it in space travels. Because when antimatter particles interact with matter particles, they annihilate each other and produce energy. This has led engineers to speculate that antimatter-powered spacecraft might be an efficient way to explore the universe. NASA cautions there is a huge catch with this idea. It takes about $100 billion to create a milligram of antimatter. While research can get by on a lot less antimatter, this is the minimum that would be needed for application. But that hasn't stopped NASA and other groups from working to improve the technology to make antimatter spacecraft possible. In 2012, a representative from the Towery Group told Space.com that it's possible that antimatter could be used about 40 to 60 years in the future. NASA created a 2010 report, with help from the Towery Group and others, called Technology Frontiers, Breakthrough Capabilities for Space Exploration, which detailed how a fusion spacecraft could work. The design calls for pellets of deuterium and tritium, heavy hydrogen isotopes with 1 or 2 neutrons in their nuclei, unlike common hydrogen that has no neutrons. An antiproton beam would then be beamed into the pellets, which would bash against a layer of uranium embedded inside. After the antiprotons strike the uranium, both would be destroyed and create fission products that would spark a fusion reaction. Properly directed, this could make a spacecraft move. So friends, this is it for now. If you like the video, then don't forget to like and subscribe and share it with your friends. We'll try our best to bring you such amazing facts about the universe. Till then, take care and goodbye.